Welcome to Tiger Paw Academy. This video sums up 6.1 about the exponential function and its inverse. Firstly, let's take a look at the exponential function. Exponential functions have a rate of change which is proportional to the function itself. In other words, the finite differences are changing at the same rate as the y-values of the function. The general equation for this function is y is equal to b to the power of x. Exponential growth is a type of exponential function with finite differences increasing at a rate proportional to the function. This table of values shows you the relationship between the change in y-values and the y-values themselves. You can see that the ratio of the difference in y-values is equal to the ratio of the y-values. For example, 4 over 16 is 3 over 12, and 16 over 64 is equal to 12 over 48. Exponential growth can be used to model the growth of bacteria as well as compound interest. The graph of exponential growth displays an increasing curve. The curve is above the x-axis and has a y-intercept of 1, considering that anything to the power of 0 is equal to 1. The restriction on the base value is that it must be greater than 1, because if it was 1, the function would be a horizontal line and would not be increasing. Exponential decay is another type of exponential function. It has finite differences decreasing at a rate proportional to the function. In this case, the base value must be less than 1, but greater than 0. Such functions can be used to model the decay of unstable isotopes. The graph of exponential decay displays a decreasing curve. The curve is above the x-axis and also has a y-intercept of 1. It has the same domain and range as an increasing exponential function, as well as the same y-intercept and horizontal asymptote. Now let us take a look at the inverse of exponential functions. To find the inverse of a function, you must exchange the y and x values of the function. Therefore, for an exponential function, the equation would be x is equal to b to the power of y. The graph of the inverse of an exponentially increasing function has no y-intercept and has an x-intercept of 1. This is because the x and y values have been switched around. As you can see, the inverse of the function is a reflection of the exponential function on the y is equal to x line. The inverse function is also located on the right of the y-axis and has a vertical asymptote at y is equal to 0. On the other hand, the graph of the inverse of an exponentially decreasing function is decreasing. It looks like a vertically stretched version of the exponential function. It has the same vertical asymptote, x-intercept, domain, and range as the inverse of an exponentially increasing function. It is also a reflection of the exponential function on the line y is equal to x. Now let us do an example. We have the function f(x) is equal to 4 to the power of x. We know that this function displays exponential growth because the base value is greater than 1. Such a function is above the x-axis and is increasing for every value of x. Therefore, the domain would be x exists as all real numbers, and the range would be y exists as all real numbers and y is greater than 0. The graph doesn't cross the x-axis and thus has no x-intercept. Its y-intercept is 1 because 4 to the power of 0 is equal to 1. The graph of this function contains all of the characteristics which were previously discussed. The curve is above the x-axis, has a y-intercept of 0, and is exponentially decreasing. The inverse of this function would be a reflection of the exponential function on the slanted line of y is equal to x. The inverse would have an x-intercept of 1 and no y-intercept. That is all for 6.1. Thanks for watching.